TypeScript is JavaScript with static typing. Basically, the compiler knows what the variable's type is during compilation. Or to put it another way, types are associated with variables, not values. This is a type annotation for a string, and when I run the compiler, I get no errors. Now let's see how static typing is useful by updating the SomeString variable to a different type than it's expecting. Let's run the compiler. The compiler is mad because I tried to assign a number to a variable that I already said was a string. SomeString is a string, I gave it a number. Please note that even though the compiler is mad, it doesn't prevent compilation in most cases. This is because TypeScript is still JavaScript, and JavaScript types are dynamic. Basically, JavaScript doesn't care what type your variable is, but you will if it's the wrong one. Another useful aspect of TypeScript is exploring APIs with an IDE is way easier. The cool function accepts a string and a number. When we begin typing the function, the IDE helps with autocomplete, but also shows us what type of arguments the function is expecting. You can see the first one is a string, and the second one is a number. And when I run the compiler, no errors. If we pass an argument that the function is not expecting, the IDE will warn us. You can see there's a little red line right here, and there's also one on the side over here, and the error that it's pointing out will also show up when you compile. I tried to pass an object to the function that's supposed to be a number. TypeScript gives us static types. When we run the compiler, there's no errors because the compiler knows that username is a string. TypeScript also gives us inference, which just means when there is no annotation, the compiler will guess what type we want. If we set a new value for username, even though username has no annotation, both the IDE and the compiler are mad because the compiler inferred or guessed that username is a string because it was initialized with a string. Array of strings is not assignable to type string. We have to be careful because if we don't annotate username and initialize it as undefined and set a value later, like we've done here, when we run the compiler, we get no errors because the compiler can't infer what the type is. The compiler can also infer function return types. I'm just making a function that accepts a string and a number, and here's the return type. When we run the compiler, we get no errors. If we remove the annotation and run the compiler, again, no errors. But if we annotate the return type with the wrong type, the compiler gets mad because we told it the return type is a number. And it knows that a string plus a number is a string, and that's not assignable to the number return type that we specified. When we remove the return type and run the compiler, no errors. This kind of inference happens from the bottom up. The compiler knows what the return type is, bottom, based on its arguments, top. There's also contextual inference, which is top down. Let's say we have an HTML element and we want to use an onClick event handler on that element. The compiler knows the type signature for the HTML element and its onClick method. And when we run the compiler, there's no errors. If we remove the annotations and run the compiler, there's no errors. If we change the event handler argument type, the IDE will show us that ironically, there is no button parameter on an HTML button element. And the compiler will tell us that we can't define the event handler's type as an HTML button because it knows it should be a mouse event. We've typed the argument passed to the function as an HTML button element, but it's supposed to be a mouse event. And we say that the HTML button element is incompatible with the event that's supposed to be passed, which is the mouse event, and a button property does not exist on an HTML button element. So to review, contextual inference is top down. Top down. The compiler knows what the target is and its onClick method, so it's guessing what the event handler argument type is based on the target onClick signature. Vanilla inference is bottom up. The compiler is inferring what the function return type is based on its arguments. And if you initialize your variable as undefined, the compiler won't be able to infer what the type is. Annotating a variable looks like this. Annotating a variable to have more than one type looks like this. Thing is a string or a number. This is called a union type. And a union type isn't just two types. It's as many as you want, within the limitations of your machine. This is cool until you want to define a function whose argument can be all of these types. So let return something equal a function that accepts something who can be any of these types, and then returns something. Luckily, TypeScript has aliases. All we gotta do is change the let to type and the colon to an equals. Now let's add the type alias to the function argument. Now let's call the function. Run the compiler and the code, and we can see that we returned a cool guy. Now you probably want the function to behave differently depending on the type, so let's use a type guard. If type of something equals a string, or type of something equals a number, or type of something equals a boolean, console log something. So here I've used the type of type guard. We also have instance of. If something is an instance of an array, we're going to join each of those things together. When you use a type guard, TypeScript knows what the type is. So TypeScript knows that something is an instance of an array, so that when I start to use something, all of the methods that are available on an array will be available. And for each, that's what I want. So for each thing, add all the things together. Both the IDE and compilers show no errors because they know that something is an array. And let's console log our join things. All right, cool. So call return something. Let's try a number. Run the compiler and the code. Sweet. Now let's try an array. Run the compiler and the code. Totally worked. The smarter way to do this would be to use the instance of array as the first condition and just use an else for everything else. All right, let's see how this works. Run the compiler and the code. Sweet. One thing to watch out for is union typing objects with not objects. Object with a name property that's a string with a not object. So here I'm going to use my type guard for the string. Type of stuff equals string. All right, the ID is cool with that. Type of stuff.name equals string. And we can see already that the IDE is pretty mad about this property right here. So let's see what the compiler says. Property name does not exist on type string or an object with name string. So clearly it exists on the object, but string doesn't have a name property. The compiler gets mad because it tries to find the best common type between string and this object, but there is no common type. You also have to watch out when union typing object literals that don't share a common parameter. So here we have two objects with different parameters. Let's make a function that accepts a thing whose type is cool things. If type of thing.name equals a string, and we can see already that the IDE is upset about the name property, but let's go all the way through to see what the compiler will say. If type of thing.id equals a number, return it. Let's run the compiler. So there's an error for each time the IDE displays an error. Here and here are these two, and here are these two. These are saying the same thing that we saw in this example, which is name does not exist on an object without a name. This one says ID does not exist on an object without an ID. And again, the compiler is getting mad because there is no common type. However, if you have two objects with the same parameter, you can access that common parameter, but not the uncommon parameters. So let's say return sat.cool or sat.lame. And we can see that the IDE is upset about the lame property because it is not a common property. But it's cool with the cool property because the cool property is a common property. So to review, a union type is defined by adding an OR pipe. A type alias is kind of like a var, except you're defining a type, not a variable. As of now, we have type of and instance of for type guards. Type guards let us differentiate between types and allow TypeScript to know what those types are. If you union type objects with not objects, the compiler gets mad. If you union type objects without a common parameter, the compiler gets mad. If you union type objects with a common parameter, you can access that common parameter. Annotating a variable as a string type looks like this. Annotating a variable as a string literal type looks like this. The string type variable can be set to any string, but the string literal type can only be set to the type value as well as null and undefined as of now. When we set the string literal type to a value that is incorrect, the IDE will alert us, as well as the compiler. Type awesome is not assignable to type miles. The string literal type by itself isn't that useful, but when combined with union types and alias types, they help document your code, catch errors, and large concepts can be boiled down to one alias. To demonstrate, I'm going to make a function that accepts a number and a string. When I call the function, I can pass any number and any string. When we run the compiler, no errors, and when we run the code, that's what I was going for. However, I can also pass the wrong string value. Run the compiler, no errors because I said any string, and when we run the code, this is not what I was going for. So, instead, let's make a type alias using string literals and union types. Now let's update our value argument to be distance metric. Already the IDE is alerting us that dragon is incorrect, and if we run the compiler, it'll say the same thing. Dragon is an unacceptable value for a type that can only be these values. So to review, string literal type values can only be set to its type, as well as null and undefined for now. They're great for documenting your code, catching typos, and prevent assigning the wrong string. When combined with union types and alias types, string literals boil down large concepts to one alias. For example, if our value requirement can only be specific string parameters, string literal types, union types, and alias types make that really easy. We can use type checking to describe the shape of a value. If we want another value to have the same shape, we could copy-paste. But already there's a parameter name problem. Superhero name doesn't make sense for a supervillain. And sure, I could update both of them, but now I gotta keep track of two variable shapes that are identical, and the chance of making typos and errors increases. So let's make an interface and update the variables with the comic book character type. Now some comic book characters' identities are known, so let's add an optional parameter. Interfaces only describe the shape of the value. We still need to set some values. If there is a typo or error, both the IDE and compiler will catch it. Types of property alias are incompatible. Type Boolean, which is what we've set our superhero to have, is not assignable to type string, which is what the comic book character type should be. Object literal may only specify known properties, and scret identity does not exist in the comic book character type. When we create a function, we can type the argument with the interface. If we remove the type from the superhero and call the function, the IDE and compiler will still catch the errors. These are the same errors as before. Object literal may only specify known properties. Scret identity does not exist on the comic book character type. Again, we're talking about the supervillain. Line 13, line 2619. This time, we're talking about the function because we still have the type on the argument being passed to the function. Types of property alias are incompatible. Type Boolean is not assignable to type string. Boolean, not assignable, type string. Our characters need an attack method. We could add it to the comic book character interface, but we might want someone who's not a comic book character to be able to attack. So let's create an interface for a function. Notice the opponent inline type. Inlining the type is still an interface, it just doesn't have a name that can be referenced, and we need these specific params if Krusty the Clown wants to throw down. Notice how we're typing an interface param with an interface. Now let's add the attack function type as a parameter of the comic book character interface. We can roll a reusable attack function, and then add some attack with params and the attack function for our characters. Finally, let's make an attack. Notice how the superhero strength isn't available for autocomplete. Let's just put it in there. The IDE is still showing us an error. Let's see what the compiler says. Object literal may only specify known properties, and strength does not exist on the comic book character type. Neither does insanity. And since we called the superhero attack function, we're seeing the error about strength again. We could add strength and insanity to the comic book character interface. However, we want to make sure that they're optional, otherwise we need to add strength and insanity to both of our characters. But if we have to add every skill and power to the comic book character interface, it's going to get pretty bloated. So let's create an optional attributes interface and extend the comic book character interface with the optional attributes interface. And now when we run the compiler, we get no errors. And when we run the code, nice. So to review, interfaces describe the shape of a value, but don't contain definitions. They can be set inline, or as a type that can be referenced, and both options are useful. Interfaces help you with typos and errors. They can have optional parameters. They can be used to type other interface parameters or extended. A TypeScript class is a function. Functions are objects, so they can have properties. Classes can also have methods. You don't use the word function or a colon when defining a class method. Just the name of the method, parens, and curly brackets. Notice that I left the opponent argument untyped. For clarity and to catch errors, let's make an opponent type. And now we create some comic book character instances. Let's have Storm attack the blob. Let's see if this works. Cool, no errors. Let's run the code. Storm attack the blob. Nice. All of the class properties are public by default. We can add the public modifier to any of these properties, but it's unnecessary because that's their default. The secret identity property shouldn't be public, so let's make it a private access modifier. You can't access private class properties outside of the class. Let's see what the compiler says. Secret identity is private and only accessible within the class. We can set the private property and have less code by setting all of the properties for the comic book character instances when they are initialized. The class constructor gets called when the class instance is initialized. Now we need to update how the instances set their properties. And to make sure that the private property got set, let's add a method to retrieve it. All right, let's call the getSecretIdentity method and see if this works. Nice. Setting the class properties via the constructor is definitely better than before. But TypeScript has a shorthand for setting property values when a class instance gets initialized. Now we can get rid of all of this code. And we can get rid of all of this code. Adding access modifiers to the constructor arguments lets the class know that they're properties of the class. If the arguments don't have access modifiers, they'll be treated as an argument for the constructor function and not properties of the class. And let's see if this works. Sweet. TypeScript classes also have static properties. Static properties are associated with the class, not the instance. Our createTeamStatic method is just returning an object. Notice that if I try to call the static method on the instance, it's unavailable. The static method is only available on the class. All right, let's check this out. Run the code. A console log is returning this object. It's got a name and an array of comic book characters. Even though static members can't be called by the instance, they can update instance private members. So let's create a private class property and set that property in our static method. Let's rename the static method to createAndAssignTeam. All right, so we already have the object. And for each member of the team, let's assign their private team property as the team object that's being created. And to make sure that this is working, let's make another method that gets the team name from the instance. We need to clean this part up and call getTeamName. Run the compiler and the code. Nice. So to review, we've learned about access modifiers and the difference between public and private. The constructor is run when the class instance is initialized, and the shorthand for setting class properties allows us to write less code. We've learned that static properties can only be referenced from the class, not the instance, and how static properties have access to an instance's private properties. We have a comic book character class that has some public properties and one private property. And we're using the TypeScript shorthand for declaring and setting those properties upon initialization. Now we need a superhero and a supervillain. They both have comic book character properties. We can use the extends keyword to inherit the comic book character class properties instead of having to rewrite the properties in the superhero and supervillain classes. Now we need an instance of our superhero and supervillain, and let's console log the instances to see if this worked. All right, let's compile and run the code. We have a supervillain and a superhero, and they've both inherited the properties from the comic book character class. So let's add some specific properties to our superhero and supervillain classes. All right, let's see if this worked. Now, our superhero and supervillain classes are inheriting properties from the comic book character class, but they each have their own specific property as well. Unfortunately, we can't access the inherited private property in the classes derived from the comic book character class, because you can't access private modifiers outside of their containing class. We could move the method to the comic book character class. And if we compile and run the code, this works. But maybe we only want to get the secret identity for superheroes. We can use the protected access modifier instead of private. Protected is similar to private because it can't be accessed outside of a class, but it can be accessed in a derived class. Cool, let's see if this works. Nice. Now let's add some functionality to a derived class when it's instantiated. The IDE is giving us some indication that something is wrong, and if we hover over the constructor, we can see that it's expecting super to be called. When you extend a class without defining the constructor, the derived class will use the base class's constructor. Now that we're defining the constructor for the supervillain class, we have to call super. The IDE is telling us that super expected 4 arguments. Okay, well, let's put in 4 arguments. Now the IDE is complaining about the super arguments, but the message isn't that clear. Let's see what the compiler says. Supercall must be the first statement in the constructor. That's easy enough to fix. Now let's see what it says. Can't find any of the super arguments. And what does this error mean? We haven't created any of these variables we're passing as super, so let's pass them in the constructor. All right, let's see if that worked. Nice. So super expects 4 arguments, because super is a reference to the base class, and the base class's constructor expects 4 arguments. We're passing the arguments into the derived class's constructor so the values can be set upon instantiation, and super can extend the base class's properties. Notice how the derived class's constructor and super arguments don't have to be the same as the base class. And yet, the supervillain class is still inheriting the same access modifiers from the comic book character class. Scarlet Witch's secret identity is still protected because I can't access it outside of a class, but I can access it in the derived class. So to review, we can set up inheritance with the extends keyword. The protected access modifier can't be accessed outside of a class just like the private access modifier, but it can be accessed in derived classes. If you don't define a constructor, the derived class will use the base class's constructor. If you do define the constructor in a derived class, super must be called before anything else can happen. We have a superhero and a bad guy. Let's make a function that saves the day if the function's argument is a superhero, and commits a bad deed if its argument is a bad guy. Our function needs to accept something that could be a superhero or a bad guy. The IDE is telling us something's wrong. Let's see what the compiler says. Something doesn't have powers. This is because the compiler is evaluating both types of the union type argument. And since the bad guy doesn't have powers, something doesn't have powers. We can get a hold of the superhero's powers property by asserting that something is a superhero. An assertion is how we tell the compiler we have some information about something's type that it doesn't. There are 2 different syntaxes for assertion. We're using the as type syntax, which goes behind the value. We're putting something in parens in order to isolate it from its property. If we remove the parens, we can't make the assertion. The other syntax is with angle brackets, and it goes before the value. The angle bracket syntax was the original syntax, but it conflicted with JSX, so the as type syntax was created. Type assertions are compile time assertions. This means that the assertion is only valid at compile time. Once the code is compiled to JavaScript, the type assertion no longer exists, because JavaScript doesn't have type assertions. Let's finish our if block by calling the superhero saves the day method. We need to add the else block, and let's call our function with both types. Let's see if it works. So to review, we use TypeScript type assertions when we need to tell the compiler that we know more about something's type than it does. They can be written with the as type syntax or the angle bracket syntax, unless you're using JSX. If we need to assert something while referencing its property, we can isolate it in parens. TypeScript type assertions are compile time assertions, meaning that the assertion only exists at compile time or in your IDE. Once the code is compiled to JavaScript, the assertion is gone. We have a reusable function that pushes something into a collection and then console logs the collection. We have two objects and two arrays. And we can just call the function with anything an array. But we're human and we make errors. What we want is to make sure we're pushing the right something into the right array. We can use a generic to tell the compiler we're going to be using a specific type, but we're not going to tell you what that type is until the function is called. This is what a generic looks like. It doesn't matter what's in between the angle brackets as long as it makes sense to you. T, which is short for type, is just the convention. Now that the generic has been declared, we can use it to type our arguments. Everything looks okay. Let's see what happens when we make an error. The type argument for type parameter t cannot be inferred from the usage. Before we made an error, the compiler was inferring the generic type, but now that we have made an error, it can't. In our declaration, the first argument is a t-type, and the second argument is an array of t-types. The t is the same type in both arguments. The first time we call the function, the first argument is a string, but the second argument is an array of objects. So this error is saying the t-types don't match. We can set the generic value when the function is called, and now the IDE shows the error. We probably want to create an interface because our type could get larger. Now the IDE catches the error, and the error message is easier to understand. So to review, generics allow us to write reusable code with types that can be set when the function is called. We declare a generic with angle brackets at the end of our function name. And then we can use the generic to declare types that will be set when the function is called. The generic can be inferred when the function is called, but it's better to set the value if we want help from the IDE. We have two regular interfaces and a generic interface. Generics make great containers because they can contain anything. We can have a container of crocodiles and a container of taxes. Maybe we need a red crocodile container and a blue crocodile container. If we want to be more specific about what we want to contain, we can use a generic constraint. The constraint changes the generic from accepting anything to accepting anything with these types. When we set the values, the IDE gives us autocomplete and tells us the types for the values. We're getting autocomplete for the property name and the value type. Again, autocomplete for the property name and the value type. One more time, autocomplete for the property name and the value type. You have to pass the type argument with an interface constraint. But if you forget, the IDE will let you know. Class generic constraints work a little differently. First, let's make a class with one property that is set after instantiation. Notice that we're not setting the constraint type. When we set the classy croc unit properties, we get the type information from the constraint. As long as the property only has the constraint type, the compiler is cool with it. If we add a property that's not in the constraint, the IDE will let us know. If we do pass the type argument, we get the type information from the constraint and the type argument. Let's make another class that uses the constructor shorthand for setting a value on instantiation. If we don't pass a type argument, we can add extra properties as long as the class instance has the constraint type. Cool, no complaints from the compiler. If we want to be more specific, we can still pass a type argument. Now that we have passed a type argument, we're getting the same level of type information from the IDE. The IDE and the compiler will let us know that likes Cheetos doesn't exist on a blue croc. So to review, generic types can contain anything, but a generic constraint can contain anything that has the constraint type. For class generic constraints, if we don't use the constructor shorthand for setting properties on instantiation, we can get away without passing the type argument, but the property can only contain the constraint type. When we pass the type argument, our property will have that value too. If we do use the constructor's shorthand for setting properties on instantiation and we want more specificity, we can pass the type argument. If we want less specificity, we don't have to. As long as the instance has the constraint, we can add extra properties.